which further led them to take these rockets to England and do a systematic study. See, Dipawali rocket is also very similar to what the old Chinese rockets were, except that the bamboo which the Chinese used to hold the pressure inside is now replaced with paper. That gives you the color that you get in a flower pot. So India's rocket industry basically started with ISRO somewhere in the 50s. Most of you might have seen this rocket being taken on a cycle, and we started with smaller rockets, SLV. SLV, the project director was a very famous name, APJ Kalam. After the success of SLV, Kalam moved over to DRDO and took charge of DRDL, which is the missile complex as it stands today. I can't exclude any engineering branch that doesn't go into it. So all engineering branches go into it, and it doesn't matter which engineer you are, you can still contribute to this industry.
Namaskar and welcome to this very special episode of the Professor Mahesh Podcast, your resource to help you make informed career decisions. As we like to think, this is your future simplified. This podcast is brought to you by IIT Madras Global, an arm of the Office of Global Engagement at IIT Madras. IITM Global is our platform to help take everything IIT Madras, our teaching, our research, our philosophy, our startups, to the world audience. Learn more about their efforts in the link in the description below. Happy Dipawali to all of you, and as we celebrate this festival of lights and festival of firecrackers, we thought it would be appropriate for us to understand a little bit about the science, technology, and this whole industry that helps us celebrate Diwali. So today's episode is an ode to all of the people that are responsible for our happiness at this Diwali time. To help us understand this space, I have a good friend and a person who has devoted his entire life to rocket research. Not the Diwali rocket kind, but the real rockets. He also has spent quite a bit of time understanding fireworks and that world. Professor P.A. Ramakrishna, Institute Chair Professor at IIT Madras in the Department of Aerospace Engineering.
At the outset, happy Dipawali to all of you also. Thank you very much, Professor Mahesh, for having me here.
Wonderful. So let's quickly talk about your own training, how did you get interested in combustion to start with, and how did you get into the world of rockets?
I did my engineering basically from the University of Mysore. So after finishing engineering, I took up GATE and joined IISc. If I remember right, I had applied to IISc Aerospace as the first choice and mechanical as a second choice, which a lot of people said why. But my passion was for aerospace, and one of my teachers was Professor Mukunda in the first semester, so he made a lot of impression on me, which made me go to him for a project, which further resulted in my doing his PhD with Professor Paul and Professor Mukunda, which was there where I was exposed to the world of rockets and also Dipawali rockets in some sense. Incidentally, Dipawali rockets has a long journey. It started with the invention of gunpowder by the Chinese.
Yeah.
It used to be just for celebratory purposes or to make an arrow fly a little longer. They would tip the arrow with a firecracker and burn it. So the basic composition has been potassium nitrate, sulfur and charcoal, which when used together will give you the kind of gunpowder composition, and that is what is being used. And it had to be in India that the rest of the rocket development took place, primarily because a lot of people might not know that we are a very, 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 very old
Rocketing nation.
rocketing nation, as well as we are a nation which had a lot of technology, which
Yes.
unfortunately we do not know of. If some of you have been to Qutub Minar, if you see, there is a Garuda Gamba of a temple that Alauddin Khilji destroyed to build the Qutub Minar. Now, in that temple, Garuda Gamba of that temple is a very, very old Garuda Gamba, which is more than 1,000 years old and is standing there in rain and sunshine without getting rusted. Now, when we had that kind of metallurgical knowledge, because the Chinese couldn't put a rocket into work in any other way other than what they were already using. So, what happens is in a rocket, the pressure builds up. So, unless you have a metal container to contain this pressure, it simply will not be able to take the higher pressures and it will burst open. So, I'm sure in the earlier world, a lot of such experiments must have ended in a catastrophic failure. But somewhere in the kingdom of Mysore, this later on found use. And because of the metal exposure to metal that we had in India, we were able to engineer a rocket that could go to 3 kilometers. That was there in Tipu's army or the or the kingdom of Mysore. Now, although Tipu Sultan, we all know, was a very bigoted person who had his own ideas about this thing, but this technology was there. And this was used against Cornwallis in the final battle. And he was very, 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 very afraid of these rockets.
Wow.
Which further led them to take these rockets to England and do a systematic study.
So, England per se didn't have rocketry before Mysore and Tipu's army used them.
Yeah.
That speaks volumes of the metallurgy and the chemistry, as you said. So let's go back to your own training and come back. And this is now, we've already come into the world of rockets and Diwali tornadoes.
Skipped a little bit.
So after IISc, I mean, somewhere along.
It happened along there was Professor Nasima, who's also a faculty in IISc,
Yes.
has written a piece on these rockets.
Remarkable man. I mean, he was the chair of the original committee that formed ISRO. And
Yes. He was also a nail director and he was instrumental in Tejas being what it is today. So he requested us to make a mock-up of that and give it to him for some this thing. So then my advisor, Professor Mukunda, turned to me and asked me to make that. So that's how my exposure to firecrackers and what it is has been.
wonderful. And your transition to IIT Madras as a faculty
After that,
member?
I went abroad for a couple of years as postdoc and then came back to IIT Madras as a faculty. So 2005 I joined. It's been more than 20 years.
Fantastic. And along the way, what was the overall environment for combustion research like when you were at IISc and in your early days here at IIT Madras? Were DRDO and ISRO pretty active in these areas already?
DRDO and ISRO were very active in these areas and they were the only two agencies that you could approach for any kind of collaborative work or a work which you are interested in. One thing that I should also credit the current government for doing is they opened up this industries for other participants also, meaning the private players and everything, especially the defense sector, because of which the activity currently has gone up significantly in these two areas.
So, and the set of problems that fall in the broad area of rocketry start with fireworks, meaning if you don't understand, you can't build a simple firecracker rocket. There's no way you can build a real rocket.
The two can be exclusive.
Okay.
Because if you look at our firecracker industry, they've not had any inputs from an serious academic or any other sort. They have done their work independent of us and they seem to be doing well.
But my point is, I think if a country cannot build its own firecrackers, there's no hope of them building a rocket for sure.
Yes. Yeah.
Right? So it's probably a simple thing. Let's come to the chemistry of fireworks. Let's understand what is a rocket. Diwali. Let's focus on a simple Dipawali rocket. What goes into making Dipawali rocket what it is?
See, Dipawali rocket is also very similar to what the old Chinese rockets were, except that the bamboo which the Chinese used to hold the pressure inside is now replaced with paper. So if you look at it, they wrap the paper around a small amount of gunpowder. A lot of people will think that there's too much of gunpowder that is being used and it will pollute and all that. It's hardly 3 to 5 grams in a small rocket that is used. So collectively, even if you buy for 10,000, you might not have taken up 1 kg of gunpowder in all that. So it's not a lot of gunpowder that is there in one rocket. It is hardly 3 to 5 grams. It produces a thrust of somewhere around 5 newtons.
5 newtons, okay.
A very small thrust, and because it's all made of paper, it's a very, very simple and elegant design. Basically, it's a paper wrapped around it, and you have a thread that is dipped in the same composition so that it ignites fast. So when we light that wick, it just transmits the fire to the propellant, and the propellant takes off. So if you open the all the paper cladding on that, you will find they also have a nozzle.
Ah,
Yes, and all of it is made out of cardboard only, and they have a cardboard long stick that acts as a stabilizer so that the rocket goes straight. So it's a very simple thing which uses all the principles of rocketry, but yeah, they've developed independent of us.
what about a firecracker?
As opposed to this, a firecracker is in a rocket, you are allowing the flow to go out through a certain open. So the pressure doesn't build up. In a firecracker, what they do is they basically plug that place and make sure that the exhaust doesn't go out. So when the exhaust doesn't go out, depending on how well you package the paper wrapping around it, it will burst open. And that is the one that produces the sound that we hear a lot during these.
So a firecracker that produces a small noise versus a, loud noise. Is it only in the wrapping or is there more?
So if you look at what we call as the atom bomb.
Ah, yes.
So that is very similar in nature, but only thing is, if you open it has some green windings, if I'm not wrong. And what they do is they have a small box of gunpowder in it, and to that composition they add a lot more fine aluminum to it.
Okay.
You can look at it as something that will go to very high temperatures and very high pressures. So they need to kind of pack it very well.
Okay.
So what they do is they pack that box with all these threads, so it can withstand much higher pressures than what the paper alone will be able to.
Okay.
So when it bursts open, it gives you that loud noise that you hear with the atom bomb.
Okay. Let's step back. What is the quote unquote fuel and the oxidizer? Are they separate or is it part of that same mixture? What's the chemical reaction itself?
So what you have in a gunpowder is typically potassium nitrate. Potassium nitrate is the oxidizer. They also add sulfur, which also is an oxidizer. Sulfur, after all, is after oxygen in the periodic table. So it's also a very good oxidizer. And charcoal is the other fuel. In some compositions, like what I said about this atom bomb, they add a lot more aluminum. Incidentally, we also add aluminum in our solid rockets. Yes, we use in ISRO. So basically to get high temperature and all that. One is a very thought out process. The other one is a very intuitive process. In India, we've been, as once I heard Professor Narasimha say, we've been a nation that looks at things based on prayojana. What is the utility in it for me is all that we.
He's written an article in Nature on exactly that, the utilitarian view of Indian science. Yes.
So we must have looked at it and said, if you add this, you will get this. But I don't care how it works in other systems and other things. So that's how the firecracker industry went that side. But essentially, this is the oxidizer, potassium nitrate, and fuel is charcoal and aluminum.
How do we get colors in a firecracker?
They add a little aluminum can give you one color, then beryllium can give you another color. They are all added in very, very small quantities. So these colors are added in very small quantities so that they give you different colors. Some of these compounds are banned, so they don't make use of it anymore.
Okay, but these are just like powdered metals.
Very, very small quantities, so that gives you the color that you get in a flower pot or a sparkler. Sparkler is basically aluminum. But other colors, sometimes they add other chemicals to boron and other things in small quantities, magnesium, to get different colors basically.
And there are these firework displays that seem to be coordinated in time.
Yes.
How do those manifest?
That now uses more electronics into it, and
Really?
that is how they are coordinated. You can use either electronics or you can have a very precise wick timing, because wick will burn at a certain rate. So if you know the length of the wick, that you have placed, you can get a very, very coordinated thing. Or otherwise, they might use electronics, which might be much more simpler for our current generation to work with.
Sure, sure. So let's talk about this firecracker industry itself. And it's a fairly massive industry, particularly in Tamil Nadu, with Sivakasi being the home of one of the largest firecracker industries. Tell us a little bit about how that grew and what are the kinds of jobs? I mean, there's of course manufacturing, but have you had any interactions with companies from there, and what do they do? What are they like?
This firecracker industries is a very big industry in itself. If one goes to Sivakasi, they'll find that entire town is all employed in this, mostly employed in this industry. One of the reasons why Sivakasi grew to be that is it's a very dry place, wherein the annual rainfall is somewhere around 30 to 40 centimeters. And it's a very dry place, which is essential for this kind of work. If you have a very wet place, then the whole mixture will become soggy. They absorb a lot of moisture and it won't fire when you ask it to fire. So that is one nature given place that is very dry, and that is how it picked up. Basically, they all picked it up from what they say as something in Kolkata back in the previous century. One of them, I think, Shanmugadas, I think, or I don't recollect the name correctly. Sure. So he went to Kolkata, brought that technology from there, and started their fireworks. Fireworks, we might think is like, anybody and everybody can do it. No, they have very strict rules for it. And you have to have a lot of distances between each of one of the plants. So they have to adhere to all of it. I've been there and looked at it many times. So contrary to our beliefs, sometimes that is of a little spurious nature and a kind of a manipulated nature, wherein we are told that child labor is there. I have not found any child labor in all of these visits that I've had, and most of them have been random timed and not. The other way to look at whether that industry has this kind of child labor or not is to look at the accidents and find out if any children have died. We hardly find any children dying in such incidents. And it's also very, 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 very risky business, and you cannot entrust a child to do that. A child's curiosity will always make it go in the wrong direction. That is something that will cause a very catastrophic damage. So they do not want to have that, because they have to stick to protocols that are well laid out. And there is a government agency named PESO that gives them the licenses. It is a very well controlled activity rather than a uncontrolled and something that is going on as a cottage industry. They have to have very large land mass to have these factories. Few acres is minimum that is required. They've been doing this for ages. I mean, more than 100 plus years now.
Are these somewhat automated, or is there still a lot of manual work that goes?
Most of it is manual. Although there is a process control, it is not as strict.
So also it's for the volume, and generally also it's a very safe industry, meaning they operate, like you were saying, against very strict safety protocols, and they're very conscious of that.
Yes. All the big industries that are doing this in Sivakasi, if you go and visit them, there are a few of them. They basically started out as family enterprise, and each family getting split, it kind of grew forward. So they have very strict protocols to follow, and they do follow that very rigidly, because if you don't follow those protocols, you'll end up in an accident, which means loss of lives, which you have to pay compensation and other things. And in addition, productivity will go down, and which again is something that they wouldn't want.
We didn't talk of one component of a rocket. What holds all of these components together? Is there a binder?
What it is done is it is a little cold pressed kind of thing. I mean, we just kind of put them all together, powder and compact it.
So there's no additional binding resin or polymer that holds it together.
Right. No,
but now we'll come to real rockets, and so the whole mentality to make a firecracker, and the mentality to, let's say, either make a tank shell, or to make a rocket also, let's say a PSLV or a GSLV. The whole mentality is the same, meaning this set of safety ideas that you should have. They're all translatable. So as a country, we've owned this for a very long time.
Yes.
That's, I think, where we take that's the starting point for a DRDO or an ISRO to really start building. So now let's scale up to our own real rockets. And India is one of the probably handful of countries that have gone as far as in its own cryogenic engine and to be able to put a geostationary satellite configuration in the air or in the space. Tell us a little bit about a basic rocket. Start with a sounding rocket, and then we will
Yes.
build on.
So India's rocket industry basically started with ISRO somewhere in the 50s, where they got sounding rockets from Germany and they tested it out and then started working on it. And it was a polymer, then ammonium perchlorate as an oxidizer, and the other one was aluminum that they added, and they made these rockets. Most of you might have seen this rocket being taken on a cycle, and that is something that we started with very humble beginnings. Very recently, I was called when I was 50, that when it was heartening for me to have gone in from IIT Madras, that they were commemorating the 50th year of what we call as the HTPB plant. Now, HTPB was a chemical that we had to really struggle for to get. That made us into the big gang. Now, hydroxy-terminated polybutadiene, as it is called, is a chemical that is used in all modern rockets. And that we developed in ISRO. And if you look back at who all did it, there were 3 people from our own chemical engineering department who headed it. And they were pioneers who built this kind of plant almost 50 years back, 54 years back now. And from there, our journey started in the 70s. We started with smaller rockets, SLV. SLV, the project director was a very famous name, APJ Kalam. After the success of SLV, Kalam moved over to DRDO and took charge of DRDL, which is the missile complex as it stands today. So that is how our defense sector grew. Whereas on the other side, we went on to build bigger and bigger rockets after SLV. And that is how we have gone right up to the moon's southern surface, which southern hemisphere of the moon and southern point, Shiv Shakti as it is called, that nobody else has been able to go to.
It's a remarkable achievement, and it's owed to the whole scientific community, particularly at ISRO and DRDO. And the whole rocketing, as we now call it, is undergoing a complete metamorphosis thanks to the new space policy and what private access to rocketry and private access to space. Tell us a little bit about what you have seen from your vantage point as a result of that.
I think I alluded to it early in the talk also. It has been a remarkable change. We were like a leashed horse earlier. That leash has been removed. We are now unleashed. If you look at where we will be, give us another 10 years, we'll be a very, very major force in both defense as well as in the civilian side, that is satellite launch vehicles and other things. Because if you look at India as a country, we probably produce more than 10 lakh plus engineers every year, which is a phenomenal workforce. They are more than the population of a few European countries. And when you have such kind of manpower, because basically all these industries thrive on ideas, new ideas. When you have this kind of a manpower, we will succeed. And we have very good institutional support in terms of education, ours being one of them, and many other institutions, where you have a lot of faculty members who, because this is a very diverse area that has to bring in too many things back into one to make it work. A lot of things go into a rocket, not just propulsion alone, electronics, structures. So there are a lot of people who have to come together, and that requires institutional support, which we have fantastic institutions and fantastic faculty in these institutions who have done a lot of pioneering work in the past, which has led us to this place.
You've talked of these multidisciplinary teams. Okay, tell us a little bit about all the different branches of engineering that go in to build a rocket. So our students who are watching, I want them to go back saying, I can also be a part of a team like that.
I can't exclude any engineering branch that doesn't go into it. So all engineering branches go into it, and it doesn't matter which engineer you are. You can still contribute to this industry.
You already talked of how material science and metallurgists
Yes.
are absolutely central. Chemical engineers,
Chemical engineers, process engineering,
electronics and electrical engineers,
computer science,
computer scientists.
because a lot of coding has to be done.
Right.
Uh, Mechanical engineering. So as I said, I can't keep
So
out
ISRO today employs all of these people.
Yes.
And all of the private space sector that's going to come up will require all of these people
Yes.
as well. Yeah. So now all of the rockets that we know, are sort of the mostly solid rocket motors, but we've also now gone to build some liquid fueled motors. Let's talk about that.
So in India, what happened was we firstly came up with a solid this thing called initially SLV3. After that, we got this technology from France for the Viking engine, which was renamed as Vikas engine in our case, which has been been the workhorse of PSLV, which has been the workhorse, has made use of this Viking engine, which is renamed as Vikas engine, and another liquid engine that goes at the top. The one at the top, if you recollect, some years back, ISRO had made a record of 105 satellites, which very recently has been broken. What you need is you need to put them on the correct orbits.
Yeah.
So that is where liquid engines come. And also liquid engines have a much better performance-wise compared to solid engines. One of the performance parameters that we usually use is what is called as ISP, which is very simplistically put, thrust per unit mass flow rate of the propellant. So if you have a higher ISP, that's a very good measure. So if you look at solids, they have a lower ISP compared to liquids. So liquids are useful in that, but solids have been useful in producing a very large thrust. So that is why we use most of the first stages as solids, and then we go on to liquids because they are not capable of producing very large thrust, or they have to be clustered to produce the very large thrust that is required.
Sure.
So we make use of them in the upper stages usually,
Hmm.
so that the overall payload is quite high.
Hmm.
So in India, we've developed all these liquid rocket engines also, and all the way up to cryogenic engine. Now, cryogenic engine is something wherein we are looking at liquid oxygen and liquid hydrogen. They are the best fuel and oxidizer available. Other than probably fluorine, but fluorine is a very difficult compound to handle, element to handle. So we've gone ahead with oxygen. So liquid oxygen, liquid hydrogen is used. We need liquids primarily because otherwise their densities will be very poor, where gases at ordinary temperature. Hence the use of the name cryogenics. So when you use them, you get a very good specific impulse. And that is very much required for geostationary launches and other launches, wherein your payload can be of the order of 4.5 tons as it stands today. And with future vehicles that ISRO is planning, we would be probably going towards 6 to 8, 10 ton class of satellites that we could be able to launch.
That's the payload that it can carry.
Yes.
So just to give listeners a perspective, you said a Dipawali rocket is about a 5 Newton thrust.
Yes.
What's the thrust of a PSLV? Roughly.
So PSLV is 4.3 meganewtons of thrust.
Okay.
So it's a very large thrust compared to what it is. The other biggest rocket that we built is the GSLV.
So 4.3 meganewtons is like 1 million Dipawali rockets. Roughly.
Yes. Yes.
Okay.
So if you look at the GSLV Mark III that we built, and wherein we typically burn each solid rocket, which is like a strap-on, has somewhere around 210 or 208 tons of propellant, solid propellant. So we roughly burn it in 100 seconds. So you are burning almost 2 tons a second, and put together it is 4 tons a second. A full-grown male elephant is around 5 tons.
Okay.
You're throwing out a medium-sized elephant at somewhere around 2.5 kilometers per second from the nozzle. And that's the kind of thrust that it's going to develop.
Wow. And that's what is required to go to, many ton payload
Yeah.
kind of a rocket.
Yeah.
The biggest rockets man has ever built, okay, were obviously in the US for the largest part with Saturn and Space Shuttle main engine. What is it that, what were those technologies and where were they required?
It was a part of the, Cold War and the race towards the moon that propelled them to use that.
They were solid rocket engines mostly, or were they
No,
different in
They were also liquid rocket engines, that is semi-cryogenic engines, that is liquid oxygen and kerosene, which is used. And if you look at Russians had built a launch vehicle called Buran, which till very recently held the record for being the biggest ever launch vehicle built, which I think Elon Musk's company has now been able to dislodge, building a bigger system than that. And before that, it was, I think, the Saturn 4, which took man to moon. So those rockets, ISRO probably had one this thing that is not there till now is the semi-cryogenic engine, which I think our own institute has also been able to pitch in that. My colleague in the department, Professor Chakravarti, heads a startup called Agnikul that has developed these rockets with semi-cryogenic engines.
Yes.
So in India, if you look at it, we have all the technologies that anyone else also has. We are on par with anybody else in terms of technology wise. It's probably time, as I said, unleash. Primarily because if you look at Elon Musk, we always want to compare there. He was given these Merlin engines free of cost.
Correct.
If our startups can be given such engines and said, go do what you think you should do, we will then also be unleashing a lot of such activity in India. And that's bound to happen in time.
I think so. I think we are all moving to a little more of an open innovation model.
Yes.
Right? It's in the greater good of the country at large, in some sense. So open with some barriers and boundaries on either side. This whole endeavor, you talked of, Saturn 4, which put a man on the moon and brought him back home. We have our own Gaganyaan program. So let's talk about what is special about human spaceflight programs. Why should we do it? And what is the motivation for our own Gaganyaan program?
So when you have to put humans to space, rocket industry is a very nasty industry in terms of the reliability of the vehicles. The reliability of a typical vehicle that we put up is somewhere around 98 to 99% only, which means if you do 100 launches, 1 or 2 of them is going to fail. Now, that becomes unacceptable when you put a human being. Although, if you've seen earlier US programs, there are failures with humans on board, which has been very, very difficult for people to take. So, there needs to be much more bigger factors of safety. Aerospace is an industry wherein our factors of safety are very, very small, somewhere around 1.5 to 1.6 are very large factors of safety. So when you have to have human programs, you will have to increase these factors of safety to make them very reliable so that they do not fail. So there are a lot of checks. Although we have vehicle capability to go there are a lot of checks that need to be done so as to make sure they are foolproof. And that is where the time that is required for these programs to take off. And you asked me this other question, why should we do it?
Yeah.
One is there are a lot of interesting experiments that can be done in space. And a lot of our own faculty have been also trying to look at them because of its medicinal values. In some cases, I think Swati Sudhakar applied in your own department. She's been working with ISRO on one such this thing. Then Professor Satyan Subaya wants to do machining in space. So there are a lot of interesting experiments. I'm not aware of all the experiments that are there in space, but there are a lot of interesting experiments with interesting outcomes when we do them in space.
Yeah.
Which is where the world has also looked at the ISS, International Space Station, so that these experiments can be done.
As you said, there's a lot of ideas that we can sort of build upon when we have a human being in space. I think that in itself becomes a platform. It's a great enabler for many other ideas to now take sprout and grow, isn't it?
Yes.
So, but what you're saying is the rocketry required to go as far as a space station is within our footprint already.
Yes.
Okay, wonderful. Let's come back
There
to
was one other interesting experiment that ISRO did called the docking experiment.
Yeah.
Which is one more requisite when you have to go, when you build your own space station, you have to have a fair ability to go and dock to it and then undock and come back. So that technology has also been established. So in a few years' time, we could have our own space station.
Sure, wonderful. So let's come back to firecrackers one more time. I think when we look at this overall, the industry, the firecracker industry, as you said, they've not worked that closely with academia. What are some things that we can do with that industry, if we were to start talking a little more and, build some collaborations? Are there
Quite a lot of things that we can do.
Okay, I hope some of them listen. That's the purpose.
Yes. One of the things that we can do is, they sometimes make use of a lot of gunpowder to get some sound level or some thrust. There are things that we can do which I was initially interested when I started my career here, Professor Murthy, and I looked at some of these things. But the challenge there is, you have to do it in a very, very cost effective manner, which is a very different kind of engineering as opposed to what we do in a normal business. And you also have to be conscious of the fact that whatever that is left behind is in our big rockets. I mean, because we fire a few of them only, we do not care about the environment. But here, since you are, using them extensively, you have to make sure that they're environmentally degradable and all that. So that puts the challenge on what materials to use, and it's a very interesting engineering. If somebody can take it up, I'm at a stage where I cannot take it up. But if somebody can take it up, there is a lot to do. We can certainly reduce the amount of propellants that go in, and therefore the other side, that pollution, that is always a factor that can be also brought up. But we should start looking at it very carefully and as a problem. And I remember when I started my career out, there was a BTech student who did a BTech project on this, and a lot of my colleagues in the department also made fun of me in that sense that what sort of a project is this?
No, I remember some of the projects that your students worked on.
Yes.
And I think they were sort of hatke, as the Hindi word says.
Yes.
Why are we here for if not to do hatke things, right? So, we talked of Dipawali rockets, 5 Newton and 5 meganewton roughly, the ISRO style rockets. But there are a lot of rockets in between. It's not just 5 or 5 meganewton. So let's talk about the shoulder launch rockets that the army uses. There's tank fired armaments. Talk a little bit about that industry and that technology as well.
So some of these smaller rockets that you talked about are, one of them is a shoulder fired rocket. There are two kinds of shoulder fired rockets. One is Igla, the Russian variant, and there is also an equivalent Afghan terrorists and others carry that short pitted. There's another missile that they carry, which is a US origin or a NATO origin. Now, these are also very challenging this thing, because you have to fire it from a human. And please remember, the human will have to take that hot exhaust, and it can burn up people. So what they do is very interesting things that they do. They have a small rocket that pushes it out first from the launcher, and then when it comes out, it has to go a certain distance away from the launcher and then fire up the other one. So there is something called a delay fuse that ignites the other one a little later. and then it has to be stabilized in air because it's traveling without any great propulsion system.
Does that kind of a rocket have any electronics on it, or is it just purely aerodynamic?
No, it has a lot of electronics.
It does have it.
It has to have a seeker which can seek out the aircraft and destroy it, or a tank.
Yeah.
So it has a lot
But
of
for the trajectory and guidance itself, it's more or less ballistic.
No, it's not ballistic.
It's not.
The ballistic ammunition is the artillery shells and some of the tank ammunition. These are not ballistic. These are guided.
Okay.
So when you come to tank, when you come to artillery, this thing, which is a ballistic trajectory. Basically, a lot of you might have looked at it as V square by the G as the range of these projectiles when you do at 45 degrees. And so, it's a very, very interesting problem. A gun is a very, very challenging engineering problem because the projectile that comes out of the gun has to be capable of withstanding more than 12,000 to 20,000 Gs, depending on the gun system that you use. Its RPM is around 15,000 RPM. So it's more like a gas turbine RPM that we are going into. And with all this, it comes out of the gun at a very high muzzle velocity of around 1 kilometer per second max. Takes the projectiles up to something like 45 kilometers range, and they are completely a ballistic trajectory.
So all of the firecracker industry is still more or less tied to the same gunpowder idea. What are some new materials that you have seen in other countries or in other industries that can be brought into the firecracker business?
One of the things that probably is a very, something that we always sense when there is a firecracker lit up is the sulfur.
Yeah.
The sulfur dioxide is, if you look at all the other chemicals, NOx and other things, they are very small compared to the other pollutants that we already have and which are there in the same. But when you look at sulfur dioxide is a very, very, very polluting this thing, because when it combines with water, it can form sulfuric acid or sulfurous.
Sure.
So that is something that should be reduced or avoided if possible. And I'm sure if so many people work on it, they can come up with a composition and develop compositions without it.
Are there polymers, energetic polymers that can make it easier to manufacture?
No, that would become more expensive.
That's the only problem. But hopefully, the technologies are there, but the scale has to reach a point where they become more affordable. Right?
Yes. You won't also sometimes want to do that, simply because, it could also accidentally get into the terrorist hands, wherein you could use this to make a rocket. You could use the other one also to make another rocket. So, which is where probably the distinction is kept, so that the smaller rockets are smaller rockets and they don't get into wrong hands, rather than the classified materials that we use in the bigger rockets.
So in this, let's talk for the next maybe 10-15 minutes about this whole broader space of defense technologies in India. Everything from, we talked of rockets and the aerospace related technologies, but def tech in India is now undergoing an absolute upheaval.
Yes.
Tell us about what are the kinds of opportunities that a young student, a young man or woman in a college somewhere can look forward to in the next 5-10 years.
First thing is, I really envy them. Because when you and I finished the PhD and went out to the job market, the kind of scenario in India was a very, very different one. Because we were not a big economy then. That economy size also brings in something. We are now on the verge of becoming the third largest economy. So we will have to take leadership. We no longer can say we are the fifth country to do this. We are the fourth country, fifth country to do this. We have a fifth country syndrome in India. You have to come out of that. Coming out of that is not going to be easy unless the next generation and the current generation kind of work towards it in a very, very dedicated manner. There's a lot to do. And if you look at the current geopolitical situation, a very, very fluid situation wherein you don't know who's your friend, who's your foe. It can change very dramatically and very quickly, which makes it for a country of our size to be independent of the influence of others. That is where the slogan of Atmanirbhar Bharat comes in, which means that we depend only on ourselves. So our supply chain and other things are established. If you look at our procurement of weapons and weapon systems, it's a few lakh crores every year. So when we have to procure them from everything from inside, ultimately, or very small portion from outside, that's a huge job market that is going to get created because of this. And if you look at the defense technology, one of the things that has kind of revolutionized now is the drone or the UAV technology.
Yeah.
Which is also going to be a very pivotal one in the coming decades. And we've also started a online BS program in our department named as UAV and Space Program. So the requirement is going to be huge, and most of this requirement might not come from the government as such, as in the government is not going to make them and produce them and things like that. It's going to be produced in the private industry, wherein innovation and enterprise is very important, and that is the one that demarcates things. So when you have that environment setting in, you have a lot of opportunities. There is no dearth of opportunities that is going to come up in the near future. Only thing is people will have to work hard. And
What can they do in college to prepare themselves for careers in this defense technologies space?
One thing that I would like to tell them is the world has a lot of opportunities, but please also stick to your academics and know them very well, because that is the one that is going to help you in the future. First, concentrate on that academic part. Whatever department you are in, it doesn't matter. You can get into this industry. The other one is keep a general awareness of what is happening. You might find interesting things that appeal to you, and you could get into that at a later date. To a lot of people, a lot of other things happen, and I mean, instead of whiling away your time on some things, first concentrate on academics, and then look at what interests you, and try to kind of focus reading or collecting information on such things, so that at a later date when you come out of college, you can either have a startup or you can join a startup and take it forward, these kind of things, or join the industry as such and go forward.
There is a lot of activity even in the startup space, as you said, in the broader area of DevTech.
Yes.
And programs like IDEX have made a massive difference to seeding and growing that sector. Tell us a little bit about, again, some ideas that you are seeing that startups are working on in the DevTech space. Drones is, of course, one very active area.
Yes, there are a lot of ideas that people are working on, many different areas, and there is nothing that is enough. One of them is decoys that we are ourselves working on. The other one is on engines for these kind of things, increasing battery life, battery management, coming up with new kinds of propulsion systems. There are a whole host of things that people are doing, which is very interesting and very absorbing. And in electronics, there's a whole host of things that you need to do, because you and your adversary are also doing the same things. And it's always you have to be one step ahead of the other to beat them in the game of this thing. So a lot of things in detection of incoming drones is required. And that's a space that we have to look at filling. And there are a lot of opportunities. And very recently, if you recollect, the Chief of Army Staff, General Upendra Dwivedi, was here to inaugurate this Agni Shodh.
Yes.
Which is located in our research park, which looks at bringing together 4 different set of people, that is academia, industry, startup, and the services. So right now the army has opened a center here. I'm sure this is this thing that is going to be replicated in many places later on.
Sure.
And we could find a lot of technologies homegrown that are going to be in use in the coming years.
Sure. Before we close, we have to talk about 2 topics. Operation Sindoor was a success thanks to BRAHMOS. It was a game changer in many ways. Tell us a little bit about what is BRAHMOS.
Okay. A lot has been said already in the open domain, but BRAHMOS is a supersonic cruise missile. It stands for Brahmaputra and Moskova, 2 rivers. it basically evolved out of an afterburner. That is, afterburner of a gas turbine engine is the backbone of it, and that was converted with an intake into what is current day BRAHMOS. So it was a collaboration between India and Russia. So this missile is a very unique one, primarily because it can travel supersonic and it can cruise for long ranges, somewhere around 500 kilometers. So any buildup of the enemy within that radius, you can take it out very easily. And what India has done is it has made it sea launchable, submarine launchable, then aircraft launchable, and land launchable. So you have all three services using it, and it can cruise up to 14 kilometers altitude and go to a longer range of around 450 kilometers, or it can go very close to the ground and go to a shorter range. So both options are available.
You can easily go undetected.
Yes, very difficult to detect when you're flying supersonic, because one is the Earth's curvature that prevents you from detecting it as till it comes very close. Now, when it is flying supersonic, you hardly have a reaction time to take it out, even if you notice it. So that is where it is a game changer, and that is something that we should be proud of, that we have in our services.
Wonderful. And the second point I have to talk to you before I let you go. You were at some point working on a jetpack,
Yes.
an Iron Man style jetpack. It's a rocket.
Yes.
Tell us a little bit about where that idea came from.
These things are also there in other services. I mean, different armies now operate with this. The idea was to develop a platform. When you look at our country, which is a very vast country with our northern borders being always hilly in the Himalayas, so transportation of goods and people in such terrains is very, very, very difficult. Now, if you can access it through the air, it makes it very short in time, and therefore it eases a lot of trouble. So we are still working on a platform based system. One of the inputs that the services gave us was we would want the soldier to be hands free, so that if there is any eventuality, something that can be done with the hand can be done. So that is where we are going. And it reduces a lot of distance. For example, as I was telling someone, some years back, I was in Sikkim, and the place I was in, so there's a famous Shiva temple in Namchi. So it was only 10 kilometers as the crow flies. But when we had to go by road, it took 4 hours to go there. So if one can reduce that time, if we access it by air, then it reduces a lot of difficulties in reaching things, which is very crucial in a very short time. So that's the idea.
Fantastic. And these are reusable jetpacks. When they are all done, they would be
Reusable, because they are now going to be gas turbine based. That's
fantastic. So between drones and jetpacks, I think we will also have human and logistics transportation
yes,
largely covered.
Yeah.
Become more efficient as well. Rama, it's been a fantastic conversation. This is a special episode for me as well. I learned a few things, and
thank you so much for giving me this opportunity. I'm really happy to be
right, and happy Dipawali to our listeners one more time.
Yes, happy Dipawali to all of you.
This has been another episode of the Professor Mahesh Podcast, your resource to help you make informed career decisions. As we like to say, this is your future simplified. Use this information to your best. Until we meet again, be well, do good, and keep in touch. Goodbye.